Hey everyone, welcome back to episode 2, and this time we're looking at a system of two massless, frictionless pulleys. Around pulley 1, we have a string that connects mass 1 all the way around to pulley 2, and around pulley 2 we have a massless string that connects mass 2 all the way around to a stationary wall. But before we jump into analyzing the dynamics of this system, we should get a feel for what's going to happen. When mass 1 gets pulled down because of gravity, pulley 2 is going to be pulled to the right to conserve the length of the blue string, and mass 2 is going to get pulled to the right to conserve the length of the green string. It is important to realize that if mass 1 falls a distance d, then pulley 2 will also go to the right a distance d, but exactly how far will m2 be pulled to the right? Well, because the length of the top portion of the green rope is the distance between the wall and pulley 2, and the wall is stationary, this length will increase by the same distance d, which means that the length of the bottom portion, the distance between mass 2 and the pulley, must decrease by d. This means that if the pulley moves right d, mass 2 must move right double that distance, 2d. If we define our axes traditionally, that is, x going to the right and y going directly upward, this means that the distance mass 1 falls downward, minus y1, is equivalent to half the distance mass 2 travels to the right, 1/2 x2. With that in mind, we can begin to draw a free body diagram for each mass. So if this is mass 2, the mass on the left, the only force acting on it in the direction of motion is going to be the tension force from the string, and we can call that T2. As for mass 1, we have two forces acting in the direction of motion. One is the force of gravity, Fg, and the other is the tension force pulling upward, T1. With our free body diagrams, we can begin to apply Newton's second law to each object. For mass 2, it's fairly simple. The sum of forces in the x direction, which is simply T2, is equal to m2 times a2. For mass 1, the sum of forces in the y direction, which is equal to T1 plus Fg, is going to equal m1 times a1. Rearranging gives us T1 equals m1 a1 minus Fg, or simply m1 g. Finally, if we look at our original equation, minus y1 equals 1/2 x2, we will see that minus a1 equals 1/2 a2, simply by differentiating both sides with respect to time. Which lets us rewrite the original equation of motion for m2, that is, instead of writing T2 equals m2 times a2, we can write T2 equals m2 times minus 2 a1. Now, looking at equations 2 and 3, we see that we have two equations with three unknowns. We don't know a1, we don't know t1, and we don't know t2. So we need a way to relate t1 with t2. We can do this by analyzing the second pulley. We know that it can't have any acceleration, or else the massless pulley would accelerate infinitely quickly. This means that the tension force pulling it to the right, which is equivalent to T1, must balance out with the two tension forces pulling it to the left. Each of the forces pulling it to the left is equal in magnitude but opposite in direction to T2, so we will call them minus T2. In other words, T1 is equivalent in magnitude but opposite in direction to minus 2 T2, or simply equals 2 T2, which means that we can rewrite equation 2 as 2 T2 equals m1 a1 minus m1 g, and we can rewrite equation 3 by multiplying both sides by 2 as 2 T2 equals minus 4m2a1. And we can set these equal to each other. So m1a1 minus m1g equals minus 4m2a1. And solving for a1 gives us what we're looking for. a1 is equal to m1g divided by m1 plus 4m2. Now from equation 1, we can easily derive what a2 is. a2 is going to equal minus 2 times a1, so minus 2 m1g divided by m1 plus 4m2. And if we're looking for the tension forces, we know that T2 is equal to minus 2 m2a1, so T2 equals minus 2 m2 m1g all over m1 plus 4m2, and then T1 is simply equal to 2T2, which is minus 4 m2 m1g all over m1 plus 4m2. Essentially, the four equations in green are our answer to this dynamics problem. We know how each mass will accelerate and the tensions in both strings in terms of only the constants m1, m2, and g. But of course, we can also solve this problem using the Lagrangian method. It takes more time and uses calculus, but it's more mechanical and less actual thinking, meaning that we don't have to realize that T1 is equal to 2T2 because of an intricacy of Pulley 2. So let's jump right into it. The first thing we need when we're solving a problem using the Lagrangian method is to define the Lagrangian, L, as the kinetic energy T minus the potential energy V. And if you're struggling with the notation, feel free to reference episode 1 of this series where everything is explained. But moving on. Our kinetic energy T now has two components. The first is from m1 moving in the y direction, so that's going to be 1/2 m1 y1 dot squared. And the second is going to be from m2 moving in the x direction, so that's going to be 1/2 m2 x2 dot squared. Our potential energy V is going to only depend on m1, because that's what's moving in the y direction, so that's going to equal minus m1 g y1. And again, the minus is so that it cancels out with the minus 9.8 from g, and as y1 increases, our potential energy also increases. Excellent, so we have our Lagrangian, L equals 1/2 m1 y1 dot squared plus 1/2 m2 x2 dot squared plus m1 g y1. So now the second part of the Lagrangian method is to determine our constraint, which is easier now that we've already spoken about it. We know that our x2 is equal to minus 2 y1. Again, the minus is so that as y moves down, x moves to the right, which means that our constraint function f is going to equal x2 plus 2y1, which is equal to 0. Now that I've rewritten our Lagrangian and our constraint function, we can get to the calculus of things, which is solving the Euler-Lagrange equation. And so we're going to do it in terms of x2 first. So the partial derivative of L with respect to x2, and that just means all other variables are treated as constants, minus the full time derivative of the partial of L with respect to x2 dot, plus lambda times the partial of f with respect to x2. And lambda is just an unknown constant. This entire term actually is going to end up representing the forces involved in this scenario. But all that added up is going to equal 0. And so if we solve this, which is a lot easier than it looks right now, partial L, partial x2 is going to completely cancel out because L does not depend on x2 directly. And so we have minus, well, what's partial L, partial x2 dot? That's going to be m2 x2 dot, because the 2 comes down and cancels with the 1/2. And the full time derivative of that, we just add another dot, so that we take the derivative of velocity to get acceleration. And this is the second derivative of x with respect to time. And then we add lambda times the derivative of f with respect to x2, which is 1, and all that equals 0. Now we get to do the same exact thing with y1. So partial L, partial y1, minus d dt, partial of L, partial of y1 dot, plus lambda times the partial of f with respect to y1, all equals 0. And so the partial of L with respect to y1 is simply m1g, minus the partial of L with respect to y1 dot is going to be m1 y1 dot, and full time derivative, so we add another dot, then plus lambda, partial of f with respect to y1 is 2, and that's all going to equal 0. And so if we solve for lambda in the first equation, we have lambda equals m2 x2 double dot, and in the second equation, lambda is going to equal 1/2 times m1 y1 double dot minus m1g, which means that 2m2 x2 double dot equals m1 y1 double dot minus m1g. And recall that because x2 equals minus 2y1, x2 double dot equals minus 2y1 double dot, so we can plug that in, and we get minus 4 m2 y1 double dot equals m1 y1 double dot minus m1g. And we can solve this easily for y double dot. That's going to equal minus m1g divided by minus 4m2 minus m1. And so all of those minuses cancel out, they turn into pluses, and we have exactly what we had before from the Newtonian method. Sorry, this is a y1. And so we can see how from here we can get x2 double dot equals minus 2 m1g over 4m2 plus m1, which gives us both of the accelerations we needed. And we can also have a look at what I said were the force terms in our equations. And so lambda from the first equation equals m2 times x2 double dot. Lambda equals minus 2 m1 m2 g over 4 m2 plus m1. And if we look at the second equation, the force term is 2 lambda. So 2 lambda equals minus 4 m1 m2g over 4 m2 plus m1. And so what's really cool is that this lambda term represents the tension associated with x2 and m2. So that's like saying T2 is the lambda term. And the 2 lambda term is associated with m1 and y1 double dot, and so we can say that T1 is the 2 lambda term. And that perfectly matches what we arrived at using the Newtonian method without having to examine any pulleys, but with having to deal with calculus. So that's pretty much it for this episode, guys. I hope you enjoyed it, because it was a lot of fun to make. If you want to see me make any more videos or have any other thoughts, feel free to let me know in the comments below, and I will see you all next time.